A caliper such as this is a fantastically useful measuring instrument. However, it can fairly easily reach its measurement limits when it comes to some common everyday measuring tasks, such as measuring around pipes and tubing such as this, or measuring threaded fasteners in general, screws and bolts like this, especially the threaded bits. You might be thinking, wait a minute, mister. Calipers were invented to measure round pipes because they work about 1,000 times better than rulers, and you are absolutely correct. So what am I talking about in this video? In this video I'll explain exactly what those measurement limits are, because it still does matter where you measure, what you measure and how you measure. By measurement limits I mean geometric limits to the caliper. So in this video we'll take a look at the caliper's shapes and surfaces and functioning parts and how they meet and how those shapes function together with or interact with round items. Okay? In this video I'm not considering limits of a caliper such as structural limits. We're not going to bend, damage, destroy or explode a caliper, although fun, or not considering some other measurement limits such as when the pipe is bigger or longer than the caliper, although clearly a limit, but not those kinds. We're going to be doing some geometry around the caliper's parts. Let's get started with the first task. You might be tempted to measure the caliper's outside diameter, and I have no problems with that whatsoever. Calipers were, in fact, you're absolutely correct, designed to measure the outside diameter. Now, based on this previous success, you might be tempted to measure the pipe's inside diameter using the caliper's spurs, these pointy bits here. And that's a no-no, and that's a problem. This measurement will be inaccurate. I'll explain how and why. And you might be also trying to measure the caliper's wall thickness using the pipe's wall thickness using a caliper like this. Also a no-no. Let me explain why. And for that, let's take a look at the surfaces on the caliper a little bit. Just briefly, I'm going to zoom in. And this is going to be like you've never looked at a caliper before. On a caliper, for measuring, let's start with the wall thickness on the pipe. These jaws are used to produce or attempt this measurement in measuring the wall thickness of a pipe. And even though I can try to zoom in, the picture is going to be imperfect because of one side is well lit and the other one is in shade, so you can't really see the geometric detail. The caliper's geometry is important at this point, so let's take a look at the jaw. On the jaw, two jaws on the caliper, they meet along a line there in the middle. There are beveled surfaces at the ends of the jaws, and those opposing bevel surfaces also meet there at the end. As well as there is this gap here, that's an intentional gap. I'm not going to tell stories about it, but that gap is there. And it's important that it's there, and it's not really, it's part of the jaw, but you see when the caliper is closed it still forms a gap. That's all I want to say about it. Now when I rotate the caliper sideways, you can see how the surfaces change a little bit here where they actually meet, where the jaws hit. Okay, you see that the jaws have some thickness, and the jaws are flush when they meet. It will be important later. And if I rotate the caliper's jaw out and up a little bit, so you can take a look at this surface here along which the jaws meet, you can see that it's rectangular and shiny. And let me just try to focus the camera. Yes, so it's rectangular and it's important. What you're seeing here next to is half of the oval shape or hole, and what you're looking at here is the bevel end on the caliper. Will be important later. So let's get started with this rectangular feature there, against which the other jaw closes, just like so. There, and we're back to normal, the shape that you normally look at. So I produced another image of this interaction between circle and caliper jaws, and it looks like this. This circle here replaces the pipe in cross section. That would be the pipe's wall thickness, and this rectangle would be one caliper jaw. This one would be coming from the outside and is clamping onto the pipe from the outside and is contacting the pipe at the red dot. It's a tiny red dot, but it's a one point of contact because you have a little gappage there and another even little gappage there. The gap is not a problem, so I'm going to get rid of the gappage or the arrows indicating the gap. Just keep an eye on that red dot. To measure the wall thickness of the caliper, the inside jaw comes and closes in, or the jaw that's placed inside the caliper, and when they close they stop at this distance from each other because the jaw that's on the inside of the pipe hits the pipe's wall there at those corners that I indicated. That's a problem. Why it's a problem is because the measurement should be taken between the caliper's jaws from that red dot to this red dot here along the edge of the pipe's wall, instead of this distance here that's now indicated by this red arrow from red dot to red dot, which is the pipe's actual wall thickness. What's being measured now is from caliper face to caliper face. Between the two rectangular faces, the blue arrow now is longer than the red arrow because they can't close enough. There's always going to be this green gap now that I filled in with green, and it cannot be eliminated. It's a geometric necessity that the jaw, the rectangular jaw profile on the inside would hit the wall at the corners before it could hit at the correct green dot, opposing the contact point from what's being caused from the jaw on the outside. See, this situation doesn't improve with the size, with changes to the size of the pipe if the pipe gets smaller. So I'm going to shrink down this image to a smaller pipe size, such as that, and you can see that in this setup the outside jaw contacts the pipe at that red dot, and the inside jaw here again contacts the pipe here and here. Instead of measuring between the two red dots there, you will be measuring from blue surface to blue surface. So that's what the problem is with using a caliper trying to measure a wall thickness of a pipe, and it's especially exaggerated or especially bad when the pipe is small, such as this. So what can you do about it? You can do two things. Option 1 and option 2. Option 1, you can get a micrometer with a pointed tip where the two pointed tips come together, really ending up in a needle point, like literally, unlike the caliper's edges, which are rectangular. These are actual needle point and like conical, and that is an appropriate tool for it. So get the right tool, or you can look up the pipe's wall thickness in a document called pipe schedule. The pipe schedule is a real document. I googled some, and no, this one here. I typed in metric pipe schedule over here, and these are all pipe schedules. I don't want to open any one of them. There are different pipe schedules for metric and different in inch-based pipes. They all list the pipe's outside diameter, inside diameter, and wall thickness in actual sizes and in nominal sizes. So either one of those options could work more accurately than trying to measure with a caliper. If you just need a rough measurement or a rough estimate, sure, go ahead, go with the caliper. It's gonna be better than nothing, but in this case actually a ruler might just work better than the actual caliper. A ruler that you can put along the edge of the caliper just flat. Oh, sorry, wrong picture. This one. just a plain ruler lash, just like that, and rotate it as it is needed, there, or place it as it is needed and read off your millimeters, whatever. It might work better than trying to measure with a caliper. So that's geometric situation number one. And the other task was to measure the pipe's inside diameter. That doesn't work with calipers either really well, and that has to do with the caliper's spurs. Let me show you the spurs on the caliper. It's gonna be on the document camera. So this feature here, what you're looking at are the spurs on the caliper. You can see it's got a beveled surface there, and on the other spur the beveled surface is on the opposite side. So I'm going to rotate this thing around. There, the beveled surface is now here on the other side. These spurs glide by each other just like so as they open. So when you try to measure a pipe's diameter, like so, inside diameter, you see this is how the spurs work. Now the problem with this lies with a geometric detail. What happens when the bevel edge on the spur meets this bevel edge that you're looking at meets the flat surface that forms the backside of the spur. The bevel does not form a knife's edge. Instead, what you're looking at here, it forms a thin, shiny, rectangular surface. I'll try to zoom in just even closer, just one more time. See if I can keep this steady enough and sharp enough so the camera can focus and you don't get too dizzy either. There, what you're looking at is this rectangular surface. It's long and skinny rectangle. Right next to it, hereabouts, we have another oval shaped hole between the spurs that are located there. But that rectangular surface that forms here is what produces an inside measurement when an inside measurement on a round object is attempted, like so. So let's go back to the other view where I can explain what's wrong with these spurs trying to take a measurement. This one is the cross section of one of them. This is the beveled surface. This is the flat backside, and the beveled surface sloping down to this rectangular area there. That's what you're seeing. So this is a spur in its cross section. As the spurs move across, this is how the caliper is closed, with the spurs just overlapping a little bit as they open along the diameter. The green line is the pipe's diameter. This is what happens with the spurs. They open and they hit the pipe's sidewall in this geometric configuration. You can see well enough that the red arrow there indicates another air gap, and that red arrow also indicates another air gap. The problem with those gaps are that the caliper contacts the pipe there, and actually let me get rid of the red arrows there at that red dot and at that red dot. So instead of measuring the length of the green line in the middle of the picture, the true inside diameter of the circle or pipe, you're going to be measuring from this red line to this red line, because that's where the caliper jaws ends, and you'll be measuring a shorter distance indicated by now the length of the red arrow. The difference between the length of the red arrow and the length of the green arrow is not much. Is that little white air gap there and that little white air gap there. It's not much, but it affects accuracy. And the smaller the pipe, the more this gets exaggerated. Let me try to shrink the pipe down, just like last time, to a somewhat smaller size. There you can see caliper jaw number 1 hitting the sidewall of the pipe there at the red dot, and caliper jaw number 1 is now vastly oversized, but you get the idea. In a smaller pipe, this gap here, this length of the green line here, there, gets unmeasured or unaccounted for. That's why the spurs on a caliper are fantastic to measure inside holes that don't have curved walls. Okay? So if you're measuring a rectangular recess with straight walls, that's where these spurs work fantastically well, but not so much when it interacts with circles like so. Okay? What you should be doing again is you can get a proper micrometer with pointy tips that actually measure from sidewall to sidewall. So that's option 1, proper tool or right tool again. And option number 2 is the same as the previous one. You can look up the inside diameter in a pipe schedule. Same stuff in the same pipe schedule. You can find the numbers. Pipes are standardized, metric or inch based, it doesn't matter. Wall thicknesses are standardized, inside diameters are standardized, and the data is available widely from either the manufacturers or from just Google it. There's lots of stuff out there. So that's what I wanted to share about pipes. Threaded fasteners are different, but in some terms similar. So let's talk about threaded fasteners a little bit. You might be tempted to measure the outside diameter of a threaded fastener. No problem with that. Outside diameter is absolutely no problem, because both caliper faces with their rectangular surfaces clamp together and create one point of contact here and one point of contact here, and those points of contact will be opposing and symmetrical to each other. No problems there. But if, based on that success, you're trying to measure between the threads with the beveled surfaces here at the ends of the caliper's jaws for tap hole sizes, that's a problem. Okay, what's a tap hole size? If you want to drill into not so much wood, this is wood, but more so in metal, but it's also the same stuff with wood. See, when you drill a hole, the drilled holes have smooth walls. They don't come pre-formed with threads right after drilling. Those threads need to be formed inside the wood or inside the metal somehow in order to take the threaded fastener and thread it into it. Okay, so it's a two-step operation. The proper size of hole needs to be drilled, and then the proper size of thread needs to be cut. For drilling the hole, you need what's known as tap hole size, because cutting the thread is known as tapping with a tap, of which here is a picture. You see, in metal, you drill a hole with smooth sidewalls all the way to whatever depth you like, and then you take a tap, a very sharp instrument that cuts the thread. This is your thread cutting instrument, and into the smooth sidewalls of the hole, when you rotate this forward, this will cut the thread and will remove some metal in the process, or wood if you're going into wood. Now in wood, you may not need this tapping very often. You don't, but if it's old wood, hardwood, finicky and cracking wood, you might want to use taps that work with fasteners that get embedded, or anchor bits or hardware that gets embedded in wood. You might need something like that. Okay, what I have on the next page is the same stuff in process. You make a tap drill with smooth sidewalls, then you tap it with, you cut the threads with a proper sized tap into the sidewalls, and then you place the bolt into it. You can drive a bolt into it. If you don't make a trap drill, the bolt is not going to go in. The tap doesn't just go into the solid metal or solid wood on its own. So holes are also made pre-drilled for wood as well. Okay, and those pre-drill sizes are important. Now in case of wood, of course, this tapping is not so much necessary, because the hardened thread on the fastener, on the wood screw, is going to cut the thread, and so it's a little different, but nevertheless it starts with drilling the proper size hole. So if you take it off, if you're measuring a screw or a bolt with the caliper in between the threads in such manner as to figure out the proper tap hole size, then that's a problem. In theory, or you might be thinking, well, or if you want to identify just the correct thread, you might be thinking, well, I need that measurement and I can take it with the caliper because it has some beveled surfaces obviously made for this operation. Wrong. Let me show you the surfaces on the caliper's end here, just really briefly. So this is how the jaws work, and they are flush, and those bevels are opposing each other. But when I open the caliper's jaws, you see that those bevels, just like the bevels on the Spurs, are not tapering to a knife's edge. You see this big rectangular surface here that was there for measuring the pipe continues into an even skinnier small rectangular surface here. It's still a rectangle. The problem doesn't go away. And then from this rectangular surface, the tapered bit starts. It starts sloping up, and on this side of the jaw, the caliper's jaw is flat. So in cross section, we're back to a trapezoid. I'm just going to try to get a last picture of this. Just give me a sec. There. Two trapezoids facing each other as the caliper's jaws close, like so. And the trapezoids here have a flattened little edge. And that flat edge does not work with the shapes that are formed by the threads. You see, the threads are triangles, and triangles don't work together really well with those trapezoids. Here, I'll show you what I mean very briefly here on the next slide. I have this thread made, 60-degree thread, whether it's metric or inch-based, it's the same 60-degree thread. And this is the little trapezoid shape with that small rectangular skinny bit at the top, and when it comes in to measure the tap hole size, it doesn't, it can't. You can obviously see there's a problem there, there's a gap there. The tap hole size would need to be here and here. This is the dimension you're trying to measure, because that's the size of hole you need to drill first, or pre-drill, for forming the threads. Either thread formed by a tap or thread formed just by driving the wood screw in. This is your tap hole size, or tap hole diameter, also known as diameter minor, the minor diameter on a threaded fastener. And when the other half of the caliper here closes in, that's what happens. You see, the bevels do match up with the threads, because the bevel is a 30-degree bevel. How I know is a long story, don't worry about it. And this is a 60-degree thread, so half of 60 is 30, so the bevel angle matches, but it ends, instead of a sharp point, it ends with a flat surface there that you saw on the document camera. So instead of measuring and determining the actual correct length of the red arrow, what you are actually measuring is from caliper jaw to caliper jaw, you're producing a measurement that's longer than the tap hole size, bigger. Now, is bigger a problem? Now, if it's bigger, if the hole is bigger, it's certainly the fastener is not going to split the wood when it's being driven into. But the problem with it is thread engagement. No, the bolts and screws are not going to a wedding. By thread engagement, I mean this distance here, bite. You see, there's less of a surface for the two opposing threads, the one on the fastener and one that gets made in the sidewall of the hole. this thread engagement or thread depth is gonna be less by 30% of the triangle's height easily. So, and if the thread is even smaller, I really don't want to shrink the image, but it works the same way. If it's shrunk down and smaller, this empty triangle there is even bigger. It's actually, it can become so bad that the caliper jaws ends can barely go into between the threads, if at all, in very, very fine threads. So that's why trying to measure threads with a caliper is limited. In big bolts and big threads, it's less of a problem, but in small bolts and screws it's more of a problem. You get the idea. So what should you do instead of using caliper? Yeah, well, same stuff. You can use the right tool, other way around. There, the right tool, or because threads are standardized, you can look up the tap hole sizes in charts and tables, such as these, what I typed in here. That was the pipe schedule. This one, tap hole sizes over here, and these are charts on tap hole sizes. There are different tap hole size charts for drilling into brass and bronze and copper alloys, or steels of all kinds. Just whatever material you're considering, you'll find different aluminum, whatever, different tap hole size charts on it, okay, including hardwood per wood species if needs be, or going into MDF, particle board, or some brittle materials that split right away and really unforgiving if the tap hole sizes may be inaccurate. So that's what you should be doing. Second thing that's wrong with this caliper setup, two more things. One is called cosine error, and the other one is called damaging the caliper. I'll go with damaging the caliper first. You see, the caliper's jaws are not lined up. They are not lined up because of the helical thread that's on the screw. On a screw, the mountains here don't line up with the mountains there. If they did, it would be just a ring and a valley, a ring and a valley. But that doesn't work as a thread. It looks cute, but it doesn't work as a thread. The thread needs to be offset, it needs to be advancing as the helical coils are wrapped around the shank of the bolt or the screw. You see? And because they are offset and the thread is advancing, that's why it's, when you force the caliper's jaws into the threads, into the roots or depths of the threads, the caliper's jaws will be forced out of alignment, and that doesn't add false measurement to your already bad measurement, but it's not going to help the caliper's structural integrity either. So it's a factor. The other thing is cosine error. You can see that the screw here is on an angle, somewhat tilted towards the bottom of the picture, and that's on purpose because that's how it looks like in real life. This is cosine error, and that just means, in layman's terms, taking crooked measurements. If you wanted to measure the width of this card, you could measure it with a school ruler like this. Anybody could measure it this way. Taking crooked measurements looks like this. Now, nobody in his or her right mind would measure anything crooked, but this is what's happening. That's with the screws, based on the thread's geometry, that this is a helix and is advancing as it travels around. It doesn't just go around in the same circle. So it's forcing the screw out of alignment. So instead of measuring the shortest point between that valley and that valley there, and measuring this distance here marked by the red arrow, it's making it longer by making the bolt crooked. The textbook definition for taking or cosine error is simply put over here, this. When the axis of measuring here is not being parallel with the dimension being measured. This would be the dimension being measured with, and measuring this way. So that's why it's, or measuring the paper this way. So that's why calipers are gonna be extremely limited in doing this. Lastly, I'm going to show you that this cosine error that gets introduced on account of the helical thread, I didn't just make it up, so I'm going to clamp this screw in, trying to go between the threads as much as I can. I also aligned this graphing paper here to that the lines are parallel with the bottom of the picture and the top of the picture. So this is these are my reference lines as well to line up the caliper with. There, that's how the caliper lines up. The caliper is parallel with the graphing lines, but you see the bolt. Let me just move it a little bit and try to focus the camera again. You see the bolt sits crooked, and I'm not making it sit crooked, it just is crooked on its own. Okay, in this case it's the screw head there is crooked off towards the left, and the caliper jaws you can also see, maybe if I put it exactly in the center. Let me just put it on a little pad here. There we have it. That's pretty good. If I can stop shaking the picture, I'm gonna steady it with this pipe and with this pipe over here. There we have it. You can see that there are tiny light gaps where light shines through there, and not so much there because it's that's the shady side of things, but you can see that tiny bit of light coming through, and that's exactly what I have in mind. The caliper's jaws don't go all the way to the to measure the proper minor diameter on the screw, and it's even worse with a bigger screw. Last picture on this one. It looks somewhat like this if I clamp it in with this big bolt. Just a sec, you see where it's going? There. It looks like this. Now this one is crooked to the right because it just got clamped that way. You can also see that the caliper's jaws don't line up because the thread is helical and is advancing, and so we're back in the same corner. That's why some of these measurements are, you know, you might be tempted to take just because one of them works out. It doesn't mean that other measurements will equally well work out when it comes to screws or pipes. So those are the geometric limits of a caliper, and like I said, those are the things that you can do about them to avoid